Hi, so today I want to talk about complexity of algorithms, how do we calculate it, and the use case for them. And we'll be talking about big O annotation in this particular video because big O annotation is used widely around industry, and in most of the interviews, the big O annotation talk comes up whenever talking about algorithm and comparing to algorithm to solve the problem. Now, before we understand like how the worst case complexity is calculated in computer science sense, let's understand the use case and why do we need it. Let's take an example. Suppose you have to say go from a destination A to destination B. So how exactly do we calculate? Okay, so from here till here, if I need to go, this is the route I will take. So there could be multiple routes. You can go direct route, or you can visit market and go. And so there are multiple routes there. So in our head itself we have a kind of time taken to go from destination A to B to see what route takes most time, and we compare and then we decide, okay, this is the route we'll take. It may be consciously or subconsciously, but we make such decisions. Now, when it comes to computer science, we happen to do the same. Now, to solve a particular problem, there could be one or more solutions. For example, searching for an element in an array. So there we have multiple algorithms for it. We have like sequential search and binary search. So there are multiple options. Now we need to compare like what's the complexity, how much time it will take, and then compare it. Now, coming down to time taken, like the time complexity of a particular algorithm, uh, why can't we say, okay, this algorithm will take X amount of seconds, like if the input n is 20 elements of an array, so it will take this much time. Reason being, computer science, like these things, that actual time taken depend a lot on first hardware, like what's the hardware that we are running on, and secondly also there are some software involved, like the high level language we write. For example, we write our code in Java, C++, or Rust, and then it gets compiled down to assembly language, which then gets down to machine code. Now, this compilation process is done by another software called compiler. So there are few compilers existing out there: GCC, CLang, and Rust C. So these compiler by itself could optimize a particular algorithm into assembly language, or so we cannot really say in real world that will happen. So for each compiler, if you get the same input, it's not a guarantee that the output created by each compiler would be same. So cannot do that. So we cannot calculate in exact seconds. So how do we compare algorithms and how do we commit? And that's what we'll talk about in this video. So now, in computer science, we cannot compare the algorithms based on the time taken by them. So how do we do it? We actually define the complexity of an algorithm based on the size of input and how it will grow as per in the units of the size of input. So once we see examples, like it will be more clear, but that's what we do. Like we base it on the units of size taken. Now, there are multiple notations or the multiple ways that we define algorithm of complexity of an algorithm. So one is called omega. So omega is the best case scenario. So to take an example here, like if it's an array and we are doing a sequential search and the first element itself is the one we are searching for, so that will be our omega. So omega would be O1. So we'll get like in one loop itself, we'll get the output. Whereas when it comes to uh, there's another called theta. So theta is more like asymptotic, like upper and lower bound. So it will say in the worst case it will take this much, and the worst case it will take this much, and the complexity will be always between these two. The third one, and this is the most talked about, especially in tech interviews, is the big O notation. So big O notation is used for calculating the worst case complexity or the upper bound. So in big O notation, this is defined. Okay, so big O notation is this of an algorithm. So in the worst case scenario, this is the complexity, and this is how it will grow the time taken by it as against the size of input. So to take an example here, let's look at our first analysis of an algorithm. So let's say we have a function like this, which takes us input n of size, could be any large number, and it returns the multiplication of itself by itself. So like a uh, it multiply itself, like so n power 2, something like that. So it returns that. So now if we look at this algorithm, so we have n and we return n multiplied by 2, or n times n. Now in this particular function we are not looping through it or anything, so which means no matter the size of an array, size of the input, the output will take the equal amount of time. So this is a little dangerous, but we it's more like, based on the size of input, this is how it will go. So we can always say when n is 1, so output will take 1, and n is 2, still it will take 1. So it's multiplying the number by itself. Under the hood, it might be doing different things, like assembly code might be multiplying itself, or just calculating the itself to the power of 2 or something like that. So that's why we cannot take that into account, and we just take account of this function. So n times n. Now if we see, when input n is 1, it takes time k, complexity is k. So 2 still k. So if it grows to n, it's still k. So the complexity of this algorithm is O1. So no matter the size of input, the time taken will be the same. Awesome. So now let's take our next example. So in this particular function, if we see, we are giving an input n, and in this we are looping through n, so from 1 to n, and we are just a simple statement of console.log. Now, in this scenario, we can see if the size of input is, or n, the value of n is 1, it will take one loop. And if the value of n is 2, it will take two loops. Similarly, if it keeps growing for n, it will take n loops. So in this case, the complexity is On because it grows linearly with the size of input. Perfect. Now let's take next example. So let's say in this case we have a function, and in this function we take n. If the value of n is 1, we return 1, or else we do a recursive function. We call the function again with n minus 1 plus n minus 1. So we call it twice. So which means it's a Fibonacci function. So it's like whenever the input size is n, we are breaking it down into 2 until it comes down to 1. So let's take an example where the value of n is 4. So if it's 4, we call two functions f3 and f3. Then again for f3 we call f2 and f2. Again for f2 we call f1 and f1. So you can see on each level of the tree we are breaking the problem into two parts and then going through it. So let's say on the level 0 of the tree, which is this, the time taken is 1, which is 2 to the power 0. On L1 the time taken is 2 to the power 1, which is 2, and on L2 the time taken is 2 to the power 2, which is 4. And that's how it grows with the series time series of 2, with a power of 2. Now if we take a high level example, like if it goes to n, the tree on level n will take 2 to the power n. Now what would be the actual complexity here? So we need to add all of these here. So if we add to the power n plus 2 to the power n minus 1, going on to the power 2, 2, 1, and 2 to the power 0. So if we add those, simple maths give like it will be 2 to the power n plus 1 minus 1. Now, as we discussed earlier, can we actually give the exact number or the exact time taken by the algorithm? The answer is no, because it depends on a lot of things. So we take it only on the size of input, so which is the n. So in that case, we ignore the constants. So we ignore the constants, which means if complexity of an algorithm is 2n, we define it as On. In this case, if it's 2 to the power n plus 1 minus 1, so it becomes 2n. So that's how we ignore the constants, and it becomes this. Now, coming to the next example, so this case it's an example of binary search. So in binary search we have an array. So we have an array here, and in array when we are searching, we divide the array into half. Further we divide array into half. Further we divide array into half. So we keep dividing the array. Now the if we see here for the size input, the time taken is 1 to 3, 3 steps, right? Now, the other way we can write 3, or other way we can define it is like, for the size of input 8, so it takes time 2 to the power 3, where 2 is ignored, but 3 is like 3 is the time taken, and 3 could be power to 2. So that's how we write, which means, which generalized to, for the input size n, the time complexity k can be defined as 2 to the power k. So n equals 2 to the power k. Now with the simple maths, we can actually say k comes here, to n goes here. So k equals log n to the base 2. In that case, we can just say log n. So complexity is log n. So that's what it becomes, and therefore it becomes this. Now, one of the simple ways to define this and to remember this is, if you're working with an algorithm where we break the problem into half on every step, the complexity is most likely log n. And similarly, if you're working with an algorithm where we are breaking the algorithm, like in each step we are multiplying it by 2 or increasing it, so it becomes to the power n. Similar, if you're breaking into 3, 3 to the power n, and so on. Now, another input thing, like what happens when there are more than one inputs. So how we derive the complexity in that case. So in this case, let's say we have a function which takes a and b, and it runs two loops sequentially. So when the loop a finishes, that's the when a loop for b starts. So in that case, we actually add them. So the complexity becomes o a plus b. The second scenario, it takes two inputs, A and B, but the loops are nested. Nested in the sense, for each A, it will run B from 0 to B. So it will loop through B for each A. In that case, the actual complexity becomes like B, B plus B plus B, A times, which in becomes A into B. So complexity A into B. Now, something to remember now, once you have calculated the complexity, how do we decide which algorithm to go with? I've drawn with this chart with this hands. It's a rough chart, but this is how on the high level it looks. The complexity of an algorithm with ON, log n, is the best. So as the size goes, the complexity time taken doesn't grow up that much. Whereas ON is linear, and then n log n, it goes up, n square, 2 to the power n, and the worst case scenario is n factorial. uh, Now, to say that whenever the algorithms are n factorial, we should not go with that or something. Rather, the way we should treat complexities are, whenever we have a problem, we could have like more than one solution to solve it. Calculate the time complexity of the algorithms and compare them as your expected input. So what's the expected input and how either of those will behave, and then decide which one to give, and not rather like, okay, this is the complexity, so we'll not go with this algorithm or something like that. Cool. Cool. Thank you so much. And please, if you like this video, do like, share, subscribe, and add in comments any topic you want to cover next. I'm planning to cover data structures next, so we can actually see the different algorithms with the data structure. But do let me know if there's any other topic you want me to cover. Thank you. Bye.